Okay, off we go. So here's where we were last time. So we were talking about change of variables. Remember the big idea of change of variables, that it's basically the same thing as the substitution rule, right? It's just kind of generalizing the substitution rule. I think it's easier to take a more geometric take, sort of point of view on change of variables, and so as such, I led into it by a kind of a more geometric point of view on the substitution rule. But anyway, so here we go. And the big idea is if you have a change of variables function, what we call a change of variables function, like so, that's literally telling you x and y as functions of u and v. So just plug that right on in. Right? That part's pretty straightforward, not much going on there. What is non-trivial is recognizing that we are stretching out areas. Right? So this little piece of area du dv is just not the same as its little image piece of area in the xy plane. They're not the same. It depends on g. And how does it depend on g is by way of this stretching factor. And just a quick reminder, we talked about that stretching factor last time, and it is, let's see here, it is computed by that formula, which you can write differently as that, and which we find very conveniently shorthanded like that. Right? So that's what that stretching factor is. Now, I think this is about where we left off last time, and I am going to try to motivate this notation here just a little bit. I don't think I wrote this down last time. I think we kind of ran out of time at the last second. I just want to try to point out why it's so convenient. And so keeping in mind that that's what goes here, that is, I'm just going to recopy it, partial xy, partial uv, that little notation. And keep in mind that that's part of my expression here for dA. Right? This product is dA. So let me, just for the sake of completeness, go ahead and put the du dv there. That's our expression for dA. And here's where we find this notation to be convenient. It's almost as if that cancels with that. Now it doesn't. It's not actually a cancellation. Right? This is very important. This is not a fraction. It's a determinant. It says so right there. Right? It's not a fraction. We write it as a fraction, even though it's not a fraction, because it behaves like a fraction. And this is a great little first example of how it behaves like a fraction. Right? So anyway, very common notational sort of alternative to represent that stretching factor for that reason. Okay. All right, now let's get into an example. Here we go. We have, by the way, this first example is highly manufactured. This is not how most change of variables questions are going to come at you, right? And we'll talk about more general sort of, how more realistically, what are you going to see and how are you going to deal with an actual live, real world change of variables problem. But I just want to get a win into the win column. I want to get one onto the board, right? And so I've set this up to fit the form and for us to have exactly what we need to be able to do it. So here we go. We have an integral to be computed. This integral has a domain D. The domain D, by the way, this is an integral in the xy plane. That domain is given as the image, namely it's what comes out of my function. It's the image of the unit square in the UV plane. Right, so this is the setup of the question. So notice, by the way I phrased this, it sounds like I'm only giving you the domain D, and then I'm giving you some sort of awkward description of the domain D. But if you just interpret this a little bit differently, I'm telling you the domain D, I'm telling you the change of variables function G, there it is, right there. Right, and I'm also telling you the new pullback domain in the UV plane, that being the unit square. Everybody on board? Okay. Right, okay, so, shoot, all we got to do, it would seem, is now I'm going to have to plug in, and everywhere I see x and y, I'm going to have to rewrite that in terms of u and v. We'll get to that in a minute. I am also apparently going to need to compute my stretching factor, because I got to remember to stick that in there. Again, this is the one sort of non-obvious, sort of, computationally subtle, you might say, part of how to do this change of variables. Don't forget your stretching factor, really huge point. So let's compute that stretching factor and largely plug and chug. Again, this function is given. There it is, x and y, functions of u and v. And I'm going to compute the appropriate partials of x and y with respect to u and v, keeping in mind that notation means determinant. Right? So that's just some partial derivatives. Make sure you can do that, obviously. Got lucky, and this happened to be a symmetric matrix. So if you got your rows and your columns switched, then there'll be no evidence of that in your result. But nevertheless, do be careful. This matrix will not always be symmetric like it is here. Okay. And easy determinant right there. All right. Now, here's a subtlety, and that is, how do I take this thing, for which I have an expression, and how do I compute its absolute value? I see a minus sign right here. I see potential for this to be negative. On the other hand, maybe this might be positive. I don't know. How do I tell where is this negative, where is this positive? This serious problem. Everybody see the concern we have to work out, right? You can't just throw away the absolute values. The absolute values are important. All right, how do we know? Here's how we know. What can I do about this u right here? What do I know about u? I claim what we know about u is actually staring at us right on the board already. Because here it is. There's u. I can see what my new domain is. It's that square, and everywhere on that square, u is between 0 and 1. Right there in the picture. Does that make sense, David? And likewise, this v right here, I can tell you exactly what's going on with v. In my new domain, there's v, and v is apparently always between 0 and 1. And so that allows me to draw some easy conclusions. This term right here is never bigger than 4. That means that the thing that I'm trying to take the absolute value of must always be negative. Right? Something never bigger than 4, I'm subtracting 9 from, that's going to be negative. And when you take the absolute value of something that we know is negative, the absolute value of a negative number is the negative of itself. So I actually get 9 minus 4uv here. Is everybody on board with that? All right. Now, sometimes it doesn't work out this nicely. Sometimes it turns out, and this is bad news, give me a second. Sometimes this expression here that I need to take the absolute values of, sometimes it's like, well, it's positive on that region, and then it's negative on that region. And how do you deal with that? How do you deal if it's sometimes positive and sometimes negative? And the answer is, tragically, I would have to break this up into 2 separate domains. And where the stretching factor, or where this expression is positive, then it is its own absolute values, and I would have one calculation to be done there. And then on this region, I would have a whole separate calculation. So stuff like that's annoying. I'm not going to worry about that in this course. To speak of, I don't think it's even going to come up. But anyway, that's what you would have to do. Okay. Yeah.
So just to understand, this stretching factor is whatever took us from here to here.
The stretching factor is what takes a little piece of area in the UV plane and its image, whatever that is, in the XY plane, and it's telling you by how much is blue bigger than green.
And then when we integrate it, we go backwards.
Well, when you want to replace, if you want to take whatever expression you have for that, if you want to rewrite that so that it's in terms of U's and V's, then you just have to account for the fact that this is not the green area. Yeah. This is not du dv. You got to stick in the stretching factor.
Okay.
Yeah. Okay. Yeah.
Is this like similar to like the thought process of like linear transformations?
I don't understand.
Because like you're changing like the vectors.
Oh, you're wondering about where the formula for the stretching factor comes from? It does. It's going to make heavy use of the derivative transformation effect. And I'm going to show you that calculation in a few minutes. Yeah. Right. Okay, so it's almost all over on this example. We've got our stretching factor. It's really just kind of a matter of plugging in at this point. And let's just go ahead and actually do this. Here was our original integral that we were interested in. Again, on this domain, and let's take a quick moment to recognize this is a really undesirable domain, right? There's no, whichever way you slice, you're going to hit two corners, which means you have three separate integrals. That's already triple the effort, right? That stinks. Also, these curves, you'd have to parameterize based on what this function is doing and the nature of these edges over here, and then figure out the equations of these curves. You'd have a little bit of work to do to figure out even what those edges are, right? And they're basically a bunch of parabolas. Okay, so that's actually a pretty hard integral. But what we see now is that I can rewrite it as an integral over the unit square, world's best double integral domain, right? 0 to 1, 0 to 1. And all you got to do is just plug in and insert the stretching factor. So to see that in action, let's see here. Let me, x, it says right here, x is that formula. So in my given integral, everywhere I have an x, I replace that with what it is. Right? So again, don't forget the change of variables function itself is giving you the output variables in terms of the input variables. Namely, it's telling you exactly what to plug in for x and y. Okay? So likewise, y, let's see here, I'll use y is that, and so this y here, and any others you would have, goes right there. And don't forget to insert your stretching factor, and there you go. And you have yourself a perfectly doable little integral. Now, I remind you, at a glance, it doesn't look like a win, right? If you're just looking at the algebra and you're looking at the choice between this integral versus that integral, well, the one on the right looks harder. That's an illusion. It's just a polynomial. This is actually pretty easy integral. There's not that much to it. More important point is the domain is the unit square. Again, world's best domain for a double integral. The original integral was nasty because it's on three separate domains with curved edges that you'd have to exert effort to find the equations of. That's a lot of work on the left. So this is actually a big win. Everybody with me? All right. Okay, so again, highly manufactured. I gave you in the statement of the question the change of variables function. That's not how things typically go down. So how are you going to find your own change of variables functions? Here are some that are useful. So for example, sometimes it's convenient to translate. Now this is what a translation looks like. Right? This will take any point and we'll just shift it by the vector a comma b. Okay. Do keep in mind that what we're talking about is a pullback, right? So we're mess. Let me clean up my mess here. We're talking about doing a pullback. So a function that goes this way whatever it does in the direction that it goes, we're going to be kind of undoing that. We're looking to turn the integral backwards. We're going to take whatever happened and undo it to get my new domain. So with that in mind, this candidate change of variables function that shifts by the vector a comma b, what that does in the pullback is to translate your given domain by minus a minus b in your pullback. Everybody on board with that? There's kind of an undoing aspect to this, and we've seen that kind of thing before. So likewise, we have here a stretch in the x direction, the undoing of which will squish in the x direction. And likewise, if you have a counterclockwise rotation, what that will do when you pull back is a clockwise rotation. All right. So I'm going to give you an example now of this one right here. This next example here. There we go. Okay, so we are given as our domain for our integral that it's this square right here, and it has certain corners given, and y'all can think through the geometry of those 4 points. I claim it's pretty straightforward to establish that that's a square, those corners. Is that cool? By the way, it's a good little exercise in geometry. How would you persuade yourself that the polygon with these 4 vertices is in fact a square? Something to think through. Make sure you can do that. Okay. All right. So now let me think wish list. What would I like to be the case? I mean, I've got this domain. It's kind of it's tilted. I don't like the fact that it's tilted. Wouldn't it be nice if I could do this to it? Wouldn't it be nice if I could just kind of turn it to the right? Just kind of rotate it around the origin clockwise by, whatever amount, whatever that angle is. By the way, a little bit of geometry applied to that point right there will persuade you that that angle is pi over 6. Another little trig exercise. Y'all can think that through. So I would like to rotate this clockwise by pi over 6. How am I going to do that? Well, you've got to keep in mind what I'm going to do to turn that into my new domain is actually undoing what the transformation t itself is. Right? My actual change of variables function needs to go the other way. So I want clockwise to be the undoing. That means t itself needs to go counterclockwise. Does that make sense to everybody? Said differently, I can think of this square over here as being my sort of new domain. And let's see here, let me get rid of stuff I don't need anymore. I need to be able to view my given domain as being an image, and it is. This given domain is the result of a counterclockwise rotation, purple, right? Counterclockwise rotation of what I would like my pullback domain to be. Okay, so you got to get that straight. It's easy to kind of accidentally get it backwards and rotate the wrong way. So something to always be on the lookout for. Okay, so next question, how do I do that rotation? And this rotation by an angle pi over 6, I'll remind you, rotations are linear transformations. Linear transformations are represented by matrices. And matrices have the feature that the columns are the images of the standard basis vectors. Y'all remember all that linear algebra stuff. And you can just literally apply a pi over 6 counterclockwise rotation to the 2 standard basis vectors, do a little trig, and what you'll find is that E1 turns into that, and E2 turns into that. Now that's another exercise, that's another make sure you can do that kind of a thing. It does require, well, depending on how you look at it, one way to see this requires using the angle addition formulas for sine and cosine. Reminder, I assume students know those formulas. If you don't know them, you should know them. They don't go away. They just keep being useful. Everybody needs to know those formulas. So make sure you know angle addition formulas, and make sure you can get these as the rotations of E1 and E2, and therefore this is the matrix, and therefore this as our change of variables function. Awesome. Is everybody happy, or does anybody have any questions? Everybody good? Yeah.
Is that always the transformation matrix?
For a rotation. Yeah, that's so this formula with the sines and cosines, this formula right here, is always the formula for a counterclockwise rotation around the origin by the angle theta. Yeah. And again, good exercise to make sure that you can establish that. Reminder, as always, if you are stuck on any of these suggested exercises that I give, come on into office hours. I'll be very happy to help. No problem, right? Just want to make sure y'all can do those things. Okay. All right. So so we have our change of variables function. Our change of variables function is this. We're going to have to compute the stretching factor, so we're going to need to compute the Jacobian determinant. So that's basically our formula, minus the absolute values. Don't forget the absolute values. Various partials to take. By the way, notice we are going to have to take, for example, a bunch of partials of x. Where's my formula for x? Well, x is the first output. So algebraically, it's literally the first output from my function. And that is computed as a dot product, like so, and then easy partials here. Yeah. Is that cool? Likewise for y. Okay. All righty. Now, something that is, I'm going to say, a little surprising at first glance. You see a bunch of trig and linear algebra and calculus, and with all of this going on, maybe a little bit surprising that this ends up being just one. Wow, what are the odds? Right? This stretching factor, really, all of that ugliness canceled. We got just one. What are the odds? Right? So actually, pretty good odds if you think about the what's really going on here. Geometrically, in fact, all we're doing is rotating. Right? And if you think about it geometrically, when you rotate, areas don't change. Right? Rotations are a rigid motion, they call it. Nothing gets stretched at all. So this is not just plausible, this is unavoidable. It's kind of got to be just one. Does that make sense to everybody? Yep.
So U and V here are 2 and 2?
One more time.
U and V here are 2 and, like the coordinates would be 2 and 2.
The bounds for
like
U
are
and V.
2 and 2?
The bounds for
Yeah.
U and V are, the upper bound for U is 2 and the upper bound for V is 2.
So
Yeah.
what would like U and V here be here?
What would what now?
Like U and V be here, just above, like my rotation matrix.
This right
yeah.
there? Oh, these are input dummy variables. So this is telling you what goes in to this change of variables. They're just input variables.
Oh, okay.
Yeah.
Got it. Thank you.
Yeah. Okay, so so I'm going to say expected that this should be the case, but don't forget on an exam, right? You always got to think about what is the intention of the question, right? What is the grader looking for you to demonstrate proficiency with? With a change of variables question, we're looking for you to show us that you know how to do the computation for the stretching factor. So please do show us the computation, even though, geometrically, you know what the answer has to be if it's a rotation. Nevertheless, we've got to see it. Okay, so what do we do with the stretching factor? Well, the stretching factor just goes right in there, and don't forget your absolute values. So easy to forget the absolute values. We've got to be careful about that. So what about the rest of it? Well, the rest of our integrand was this. I claim it turns into this because, reminder, for example, x is that dot product. And so this x right there is just that. That make sense to everybody? Everybody see how I got that? Likewise for y. Okay. So again, now let's look and let's try to decide, was this a win or did I just waste a bunch of time? There is that integral that I started with, and now there's this integral that I see as an alternative. And again, if you focus on the algebra, you're going to be misled. You're going to think that this integral on the right looks harder. Right? It's not. This integral on the right is way easier, right? Because it is on a nice, convenient domain, whereas this original integral we were given is on this much uglier domain where you're going to hit corners depending on which way you slice. You're going to hit a couple of corners, and that's actually triple the effort to do the original integral. Yeah.
Is there a reason as to why it's like du dv unless it's like dv du?
No, in this case it doesn't matter. Yeah. Okay. So you could do this the other way. Doesn't matter. Yeah. Okay. Yeah, totally. Alrighty. Okay, so a couple of little things that have to get said. These are, I'm going to say, kind of formalities. Technically, we need for our change of variables function to be continuously differentiable. You're not going to have any temptations to use any that aren't continuously differentiable, but nevertheless, it's got to get said. Now, here's the one that actually is potentially a little bit of an issue. This isn't going to be the focus of this course, so we're not going to have any such issues. But it does have to be invertible also. There is a nasty problem that can come up if your change of variables function is not invertible. So in other words, 1 to 1 and on 2, right? So anyway, heads up about that. And if you're curious, if you'd like to hear more about why, what can go wrong if you don't have an invertible change of variables function, come talk to me in office hours. I'll be happy to show you a counterexample. Okay. Here's a little exercise. This is just an observation, really, but if you have a change of variables function, and again, x and y being the outputs, those are what you take the partials of with respect to, of course, the inputs, which for that purple function are u and v. So there's our stretching factor. Now here's the thing, if this is in fact invertible, and therefore you can invert it, and therefore you could think of the function as going the other direction, totally could, a different function, the inverse function. Here's the thing, if I want to know the stretching factor going the other way, it's the same formula, it's the partials of the outputs, now u and v are the outputs, with respect to the inputs. And again, going the other way as we are, the inputs are now x and y. So same formula, just the variables are playing different roles because we're going the opposite direction. Is that cool so far? Okay. All right, now I'm going to make the modest observation that if you do kind of both back to back, nothing happens. Right? If I take some little region of the UV plane and compute x and y and then compute the corresponding u and v, I'm just going to get the exact same points that I started with. Nothing has happened. Grand total of the stretching factor for doing both of those together has to be 1 because nothing happened. And what that tells you then is that the product of that stretching factor and, oh gosh, color choices, and this stretching factor, that product has to be 1. And of course that means that these two factors are reciprocals of each other. So this is a really nice little result, and it is another example of why it's very convenient to write these stretching factors as fractions. Because again, they behave like fractions. This is just another example of how these stretching factors behave like fractions. I cannot emphasize enough, they are not fractions, right? This is not really a fraction. It's a determinant, right? But it behaves like a fraction, and writing it as a fraction, therefore convenient. Is that cool? Everybody happy with that? Okay. So, how is this useful, and why would I ever want the change of variables function to go the wrong way? It just turns out, the next example is going to be a great illustration of this. Sometimes that's the way that we can write it down, and sometimes going the other way can be a real pain. But going this way, going backwards, going the wrong way can actually be much more convenient. So here we go with an example. This is a weird example. This is a pretty standard example. By the way, this looks highly manufactured. This looks like made up nonsense. It isn't. This region I got here, I cleaned up some of the numbers a little bit just to streamline things, but this is morally equivalent to a region that comes up in a thermodynamics class. Y'all may take a thermo class at some point as engineers, and if you study something called the Carnot cycle or the Carnot engine, it's a theoretical engine that allows for drawing powerful conclusions about the limitations of efficiency. So it's a really big deal, one of the fundamental ideas in thermodynamics, and this region, pretty much, again, I've cleaned it up a little for convenience, this region plays a central role in those discussions. So. Okay, so anyway, in particular, you'll notice we have a couple of level sets of x, y, and we have a couple of level sets of a different function, x, y squared. And our region is what is bounded by those. So in other words, our region is this yellow thing in the middle. What a weird region. How are we going to do an integral on that region? You can slice it up, but you're going to hit a couple of corners. Whichever way you slice, you're hitting corners. So this is 3 separate integrals with bounds coming from curves with weird equations. So you're going to have reciprocals in your bounds. This is pretty undesirable. Yeah? Okay. All right. Okay, here's the move. And I did not think of this on my own. Somebody showed me this too. This is very clever. Don't think to yourself, oh man, I never would have come up with that on my own. Right. Yeah, me neither. Right? Most people don't come up with this on their own. So this is a very clever idea. Here it is. If your bounds are given as level sets of 2 functions, make those 2 functions your change of variable function. Right? So this right here that you get just by looking at what 2 functions are my boundary curve level sets of. Make that your change of variables function, and stuff's going to work out really nicely. So it's lovely how this works out. So let me show you why this works out as well as it does. By the way, first observation, I will point out that our function is, as promised, going the wrong way. Right? It's going to the left. I want to turn this domain into that domain, so this is not a pull back. This is a kind of a push forward. Right? Our formulas that we have just don't fit with this as it's set up. So that's weird. But why it's desirable, let's look at these curves, and let's see here. We will start with this curve right here, xy equals 1. That's this curve right here. Oh, missed. That's this curve right here. Well, xy equals 1. Wait a second. Xy is u. That means that its image over here is just u equals 1, which is a vertical line. Everybody see what happened there? By the way, that's why it's so important that these be level sets. Right? It's critical that these be level sets of our u and v functions, because it's only because these right-hand sides are constants that u becomes a constant over here in the uv plane. Does everybody see that? Likewise for the other curves. So yes, slick move, and again, the bad news with this slick move is that it's going the wrong way. And so what can I compute? The stretching factor that I can compute here is partial uv partial xy, because u and v are what I have. I have formulas for u and v. I don't have formulas for x and y. I can't compute from what I have here, at least not directly, partials of x and y, because I don't have formulas for x and y. Right? So I'm going to have to compute the one that I can. I can compute partial uv partial xy, and that is just a matter of computing various partials and take the determinant, blah, 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 and you get an answer. But that's not what I'm going to need. What I'm going to need is partial xy partial uv. And that, of course, is the reciprocal of what I just computed, partial uv partial xy. Yeah?
How'd you know you needed to
Do what?
change the order of it?
Oh, how do I know I'm going to need? Yeah, okay, great question. Yeah, that's coming up in just a second.
Okay.
Yeah. But yeah, that's the natural next question. Absolutely. Okay, so yeah, how do I know which one I'm going to need? And let me just remind you, here's what I was asked to compute in the statement of this example question. I want to compute, apparently, on this domain right here, I want to compute an integral of x to the 8th y cubed dx dy. This is what I want to compute. I'm going to need to rewrite, then, dx dy. I'm going to need to write it in terms of u and v, because I'm trying to get over here into the uv plane so I can have that new domain, which I love. Hey, this is a fantastic domain in the uv plane. It's a square. Constant bounds, right? Totally awesome. About as good as it gets. Let's see here. What is it? Let's think out loud. What would I put in here? What would I multiply by du dv to get dx dy? And, well, just put in here what it sort of has to be in order to get the cancellation to make it work. And again, that's not a real cancellation, but it will always guide you in the right direction. So this is a nice little memory trick. This faux cancellation here tells you, well, apparently what I'm going to need to insert here is partial xy partial uv. Does that make sense? Does that answer your question? Yeah. So I need partial xy partial uv. And that's apparently 1 over xy squared. Yeah.
I'm a bit confused as like what we're really trying to do.
Yeah, so we're trying to compute this integral on this domain.
Yes.
Right? And the big strategy was to change the variables over to an integral on this domain, and it's just a question of, well, yeah, but our function's going the wrong way, but nevertheless, I just need the stretching factor.
Yeah.
This is the stretching factor that I need in red.
To go backwards.
To go the direction I need to go, which you can think of it backwards or forwards. In some sense, the notation does the work for you in keeping track of which direction you're going.
Okay.
But I need partial xy partial uv, and I compute it here as a reciprocal of the one that was more convenient to actually compute.
So we're doing a change of variables because u and v have like constant bounds, so it's much easier.
Yeah, exactly. Oh yeah, much easier. So instead of having 3 separate integrals with non-constant bounds with reciprocals in them, now I'm going to have one iterated integral whose bounds are just straight up constants. In fact, they're integers. It's about as nice as I can get. Yeah. Yes?
Does Does this like justify what you were doing a little bit before this with the stretching factor? Like a little bit above this.
Up here?
Yeah, like.
Yeah, this is the formula that I used to. Yeah, totally. That's exactly what I used to, right here.
Okay.
Yeah. Yep. Yes.
You don't know what x and y are as a function of u and v, right?
Correct. That's kind of the problem, right? So I was able to pull this little slick move here where I set up the function going this way, and in this particular example, I could actually do the algebra and I could find a formula for x and y in terms of u and v, but I want to demonstrate the technique of how you don't even have to, because this is, in fact, ultimately easier and better.
Then how do you write x to the power of a and y to the power of 3?
Yeah, right, totally. That's the very next thing I'm going to do. Yeah, totally. Okay, so she points out correctly that when we insert the stretching factor, my new integrand with the stretching factor included works out to be this. And this is where I would normally like to plug in and say, oh, well, yeah, and x is a certain function of u and v, and y is a certain function of u and v. You plug those on in, right? And when your change of variables functions go in the correct direction, then that's all good. And I don't have that, right? So here's the good news. Technically, I don't need to know the formula for x, and I don't need to know the formula for y. All I really need is stretching factor included. I just need to know how to rewrite just my new integrand. It's x to the 7th times y. That's all I actually need to be able to convert into u's and v's. So that's the good news. The bad news is it is a problem. And here's an example. I can't give you a general method here because the algebra is different every time. The algebra is going to depend on kind of the nature of the setup of your problem. And so ultimately you're going to have to make a reasonable guess and then solve to find the particulars. That's just going to be the nature of the beast. And here's the example. Again, we're trying to figure out what to do with that. That's our new integrand. I want to write that in terms of u and v. Keep in mind u is xy and v is xy squared. And now here's where the guessing the form comes in. This is going to be you just got to make a reasonable guess every time. It's always going to be different. In this case, I'm looking at what I have, and I see a product of powers of x and y. Okay. And I need to figure out how to write that in terms of u, which is a product of powers of x and y, and v, which is a product of powers in x and y. So the question to us is, what would I think I would do to a couple of products of powers of x and y to produce a product of powers of x and y? And now, speculate as you will, right? And what occurs to me, and I think this is a reasonable guess, if I take a product of powers of these two products of powers, I know that will produce a product of powers. And that's what I'm trying to produce. So this, what I have in dark blue, seems like a reasonable guess of the form. The details, what is the A, what is the B? Oh, I can't do that in my head, right? That's something I'll have to work out the details later. But it seems like a reasonable guess of form, given what the form of u and v are, and given what the form of our integrand is. Does that seem like a reasonable guess to everybody? Again, it's going to be different every time. You won't always have products of powers. Sometimes it might be linear combinations, or could be, who knows, could be anything. Yeah.
Is there any way to look at that and just intuitively know that it's going to be a product of powers, at least for this specific example?
I mean, I would say that you can convince yourself of it being reasonably intuitive guess, right? But there is no brain off, follow this rule, kind of like it'll always work as follows. Yeah, not really. So you do have to, you just got to look at what you have and look at what you need and just think what will allow me to turn what I have into what I need, and it's going to be different every time. So anyway, I make this guess, and then it's just a matter of sort of multiplying everything out and solving for A and B, and that's just algebra. Y'all can read those details, and that then allows me to rewrite my integrand in terms of U and V as I need it to be. Okay, there you go. All right. Okay, so we've got a couple of wins under our belt now, several wins under our belt. I want to really quickly talk through where this formula comes from for the stretching factor. I kind of swept that under the rug previously. As I said before, there's a lot of stuff going on. We're keeping track of, stretching factors and which direction and various variables and bounds, and there's a lot of stuff going on, and I didn't want to get distracted by formalities. But let's see where this comes from. It's actually a pretty straightforward process to motivate. Keep in mind the idea is I have some little piece of area on the left that by way of my change of variables function is going to turn into something approximated by a parallelogram on the right, and I just want to know how much does the area get stretched out there. So, a couple observations to make. First, it's easy to understand how this vector turns into that vector. And the reason why is you can think of this edge of our little rectangle here as being a change in the input, and you can think of this edge of this parallelogram over here as being the corresponding change in the output. And what relates input changes and output changes? Well, the thing that relates input changes and output changes is the derivative matrix. The derivative matrix is what you multiply by input changes to get output changes. So that tells us that our edges here, our edges of our parallelogram have these formulas right here. Now, next thing I'm going to do is compute this area. This area right here, well, that's a parallelogram, and we have a formula for how to compute the area of a parallelogram, right? Way back, chapter 1, possibly Math219. And the formula is first edge vector becomes the first column, and second edge vector becomes the second column. And then it's just a matter of doing a little bit of algebra down here, and in particular, notice that scalars factor out. Gotta love it. Another fact of linear algebra, right? Sort of the linearity of multilinearity of determinant. And then here's a slick move. This matrix, y'all will probably recall, could be rewritten as a product like this, where those are the columns of that second matrix there. So the E1 and the E2, I can just kind of do it like this. And then you notice, hey, wait a minute, that's the identity matrix. And so this whole thing here is just DG times the identity matrix, namely it is DG. So that is just that. And lo and behold, we're done. We got exactly what we needed. Keep in mind our actual goal here was to figure out how to know what to multiply by input area to get output area, And we now have that, and there it is, as promised, absolute value of the determinant of the derivative matrix. Okay, I heard a beep, so that means time's up, and y'all have a good rest of your Monday. See you on Wednesday. Don't forget about attendance.